This is the second video on two-dimensional boundary value problem where we look at the heat conduction in a 2D slab. So the problem was the second derivative of temperature with respect to position is equal to 0, which is the Poisson equation with 4 boundary values on temperature. And the goal is to find the distribution of temperature in a 2D slab where we discretize every term in our differential equation using central difference with respect to x and y. So now I'm going to show you the MATLAB script for that. So here is the differential equation where we can simply show the geometry like this, where we have a square with temperature equal to 50 on the west and south side and equal to 25 on the north and east side. So we set up the problem, our minimum x, maximum x, minimum y, maximum y, number of discretization along the x, number of discretization along the y. So basically we have to create a grid on this 2D slab and solve for the temperature at every grid point. These are the dimension or the discretization along the x and y. So remember, after we do the discretization, we end up getting a matrix representing the linear system. For that matrix, we have an A matrix and B matrix. So first we initialize our B matrix or B vector. It's going to be 2 columns, so that is corresponding to the matrix that we created to store the information for boundary values. So the first column is going to be the boundary, is going to be the index of the boundary point, and then the second one is going to be the boundary value. So that is corresponding to this vector. I have a vector with 2 columns, and the number of rows in there is going to be, if I have nx along the x and ny along the y, so totally I have 2 times nx plus ny along the boundary, but I have double counting the corners, so I have to multiply minus 4. So I have to subtract 4 from it to basically count all the grid points along the boundary or in the periphery of the 2D slab. So that's the dimension of my B matrix. So then I go over every side, like bottom side, left and right side, and top side, and put in basically the corresponding index for every boundary point with the value. Like I can go over maybe one of them, for example. Like when j is 1, so j is 1 corresponds to, let's say, this edge, and the temperature along this is 50. So then I go here and then say when j is equal to 1, then I record maybe the row index of that point and the temperature corresponding to that point. Okay? So that's how I feel BC mat. Like in the top side, I think the way I index these points, I go right, so I go along the column first. So my indexing goes like this, so 1, 2, 3, 4, 5 all the way to m, and then m plus 1 all the way to 2m, and then 2m plus 1 all the way to 3m, and so forth. So basically I go column wise from left to right, and that's why here when j is 1, the index exactly is equal to the number of row, but then when we go to the top side, for a given j index, then I have basically the number of x points times the number of, so the discretization along the x times the previous rows. For every row I get n index, so then if I'm sitting on, let's say, row 2, then I have 1 times nx points behind me, and then you add j to that. So that's how we count the index for the top side. So after we put all this into the matrix, BMAT, then we create our x and y vector, going from the minimum to maximum x and y with the corresponding discretization. From here I calculate the dx and dy. Then the dimension for the A matrix is n minus 2 times ny minus 2, because I'm not counting the boundary grid points. So if there are nx points along the x direction, 2 of them corresponds to the west and east side, so then there has to be n-2, and then 2 of them correspond to the south and west side, south and north side, so it's going to be ny-2 to remove the bottom and top row. So then you set up the unknown list. Your unknown list is going to be, well, actually the temperatures, you need the temperature for every grid point, so that's why it's nx, ny, but the number of unknowns is actually less than this, less than nx times ny. So here's I initialize my A matrix. The dimension of the A is going to be, as I explained, is nx-2 and y-2. And then the same thing is going to be the dimension for the B matrix. So exactly as I had in the notes, we create these 3 vectors, the corresponding I index, corresponding J index, and the coefficient where we exactly know where every coefficient is going to go. So these coefficient corresponds to the I and J index of the corresponding term in the differential equation. So I have to put them in the matrix form. We know which row and which column they're going to go to. So for index IV, J index JV, then the column that coefficient is going to go to is going to be how many points you had before that point. So then there has to be number of rows minus 1 times nx, because the nx disposition along the x, and then plus the current point, the index for the I index for the current point. So anyways, you calculate the column number and you go to that row with that column, you place the coefficient, you put down the coefficient in that element. And you have to add them up, because if there's another equation contributing to that element of the matrix, then it has to be there. So that's why we add the coefficient to the current value of the element in the matrix. And then to assemble the B coefficient, then you have to go over every boundary points and multiply the corresponding A column or column of A by that value of the boundary point and move it to the right side. So then if my previous B is called B, then the current one is going to be the previous one minus the corresponding A for the column of that boundary value times the boundary value. We're going to move it to the right side, that's why there's a negative sign here. And that's going to update my B matrix. If that point within the mesh does not fall on the boundary point, then we don't do anything. So basically, we do not add that to the B matrix or B vector, we just keep it in the A. So now my A is going to be including only the columns of the original A if the index of that column or that column number does not contribute to the boundary point. So just keep it in the A matrix. So by this time I have my A and B. Then you can solve the system by A backslash B, you get the temperature, but these are the interior, you have to add the exterior temperature, and that's what I have here. But before doing that, this is going to be a column vector. Now if you want to have a matrix for the temperature, like exactly when we presented in a grid, then you have to convert your column vector to a matrix of temperature, and that's what I do here. I know the index J and I for every unknown, then I can convert that to a row and column number basically, and then put it into a matrix. So then this is to convert a vector of unknown to a matrix of unknown. But now again, it's not unknown anymore, they're all known because we just solved them, but then we have to convert the vector representation to matrix representation. And then we have to concatenate the boundary conditions along this grid to basically complete the whole mesh. So then we go over the boundary points again and then figure out basically from that B matrix back calculate the row index, and then based on that we can calculate which J index is going to be that boundary value, and then put that actually into the matrix, the temperature matrix. So by this time I have my boundary points, I have the interior points all represented by this T, I, J. So you know for a given I and J, you can exactly know what the temperature is going to be. For the corners, I haven't done the corners. This is just the boundary values and not the corners, because we said corners do not even come to differential equation and sort of useless. But if you want to really have a good representation of the temperature, then you want to add that manually into the corners. So these are just temperature in the corner for the two corners that have two different temperatures on the two sides, like for the northeast, and you have to get the average of these two temperatures. For the northeast, for the northwest, you get the average of these two temperatures and put them in here. And that's what I have the average temperature calculated for the boundary points. Then you get a minimum maximum temperature, and then you can color code from low to high, being blue to red, and then you can just do a contour plot of x and y, x of the grid, y of the grid, that we calculated using a mesh grid, and then we just put the temperature, or represent temperature at every grid point, and then we color code based on, as I said, the minimum maximum temperature that we created here. So we use color map to color code that, and if you run this, oh, by the way, so you can also use surface plot to draw the temperature based on the color code. And so if you run that, you see, so basically there is a mesh behind this, you don't see it. So here's the cold temperature, here's the hot where we're at 50 degrees, and here's cold where we're at 25 degrees. And then you see how the temperature varies, along the x and y, so from blue to red. So it's not linear because this is rectangular, but you see that, the interface between how cold becomes hot is just a, diffuse interface. All right, so that was an application of a direct method for two-dimensional heat conduction. Hope this makes it clear. So thanks a lot for watching.